Today we begin chapter 18, which is probably one of the more difficult chapters that you'll get here. We'll end in a couple of days on probably the most complicated reaction mechanism that you'll see this semester. We'll break it up into parts, so hopefully it won't be too bad. The theme of chapter 18 is something called carbonyl condensation reactions. Condensation is a reaction where you lose water, or rather where two different carbonyl pieces come together to form one molecule. But the theme of this chapter is that your nucleophile is going to be an enolate, and then your electrophile is going to be some kind of carbonyl group. So we're combining all of what we've learned so far about carbonyl chemistry and what we learned in the last chapter about enolates being nucleophiles, and we're going to put them together to form new and interesting products. Just to remind you of where we've been before when carbonyls have been electrophiles, if there's no good leaving group, that is, if it's an aldehyde or a ketone, we get nucleophilic addition reactions. If there is a good leaving group, or a good leaving group at least relative to a negatively charged oxygen, we've gotten nucleophilic acyl substitution reactions. And we're going to see both kinds of things happening with carbonyl compounds. We're going to start today with the addition reactions. Okay? So, we've said before that you can make from a carbonyl compound an enolate by putting the carbonyl compound in the presence of a base. So let's just use this standard ketone, and the ketone's got an alpha proton. We're going to use a weaker base relative to the pKa of the ketone proton. We learned in the last chapter that pKa is around 20, so we don't expect hydroxide to completely deprotonate the molecule. In fact, only a little bit of deprotonation happens. We form a little bit of this enolate. Oops, there we go. Probably, less than 0.1% of the enolate. And greater than 90%, 99% is still the starting ketone. We've since talked about some other things that can happen to the enolate. For example, the enolate might get protonated on the oxygen to give you the enol, which we've said is in equilibrium with the starting ketone. And then there's another thing that we learned way back in chapter 14 about what hydroxide can do with the ketone. You can have hydroxide attack the carbonyl carbon to give you the hydrate. So this is sort of a review of all the things we've said have been going on anyway with carbonyl compounds in the presence of this hydroxide base. Does that make sense? What we're going to add today is something that we should have been thinking about all along, but we've been pretending didn't exist, and that is, what do you think happens when you make some enolate, but most of your starting material is still ketone? Under those conditions, you have a little bit of nucleophile present and a lot of electrophile. So you can get a reaction of the enolate nucleophile with the starting electrophile, and we want to go through that and talk about that today. So what's the best way to do this? Here's the enolate nucleophile, and then here's the ketone electrophile. For the nucleophile, we expect the enolate to be nucleophilic where the negative charge is, and we've drawn a resonance structure for an enolate before. I'm not going to draw it here, I'll just draw it up top. Remember, you can draw this resonance structure for an enolate where the negative charge is delocalized on the oxygen. For the enolate, we've said that even though we like this resonance structure because it has the negative charge on the more electronegative atom, for the most part, enolates are more reactive on the alpha carbon. That reflects a couple of things. The reason for that is, first, carbon-oxygen pi bonds are more stable than carbon-carbon pi bonds, so it makes more sense for the nucleophile to attack on the alpha carbon so that the carbon-oxygen pi bond can be intact. And the other reason is, if you go and actually calculate where most of the HOMO is for that nucleophile, it's mostly on the alpha carbon. So we expect the enolate nucleophile to do the attacking from the alpha carbon. Now, if you think about the electrophile, where is the LUMO? Where is the empty orbital that's going to be attacked on the electrophile? Well, as we've learned before, the LUMO is the pi star. So you could expect the nucleophile to attack the pi star, breaking the pi bond and creating a tetrahedral intermediate. So let's go ahead and draw with the arrows using arrows being the instructions for what the next step is. Here is what used to be our nucleophile. Here's the carbonyl carbon that we attacked, and here's the oxygen. That's going to be the negatively charged oxygen in the tetrahedral intermediate. Here's the blue alpha carbon. And in red is the new bond that we made. Here is the oxygen that used to be the oxygen of the tetrahedral intermediate. Here's what used to be the carbonyl carbon, and then there are two methyl groups on what used to be the carbonyl carbon that come from that ketone. And we've made a new bond now between the alpha and the beta carbons. Okay, so that's a nucleophilic addition reaction. You shouldn't think of that as a whole new reaction. It's actually just an example of what you've seen before for carbonyl chemistry, only this time the nucleophile is a little bit different. All right, questions about that? So it turns out that this reaction is reversible. The negatively charged oxygen can kick off the enolate as a leaving group. And so anytime a reaction is reversible, whether or not it happens is going to depend on the stability of the products. In general, for the aldol reaction, for this reaction that we're dealing with, which actually happens to be called the aldol reaction, the products are more stable than the starting material, so the reaction will go forward. If we look at this negatively charged oxygen and the carbonyl carbon that it's attached to, aside from the enolate, there are no other good leaving groups. So we're sort of stuck there until until the negatively charged oxygen gets protonated. It can get protonated by the conjugate acid of our base. We used that base to generate the enolate, right, through this kind of step, removing the alpha proton. So we can generate the conjugate acid, or react with the conjugate acid of our base, generate this intermediate, and this is one of the possible products of the aldol reaction. Here's the OH group. Here's what used to be the carbonyl carbon. And here's what used to be the enolate nucleophile. Here is the new bond that we made. Here is the alpha and the beta carbons. The structural pattern you're looking for here is this is a beta hydroxy carbonyl compound. Or in other words, we will call that an aldol product. If you see a beta hydroxy carbonyl compound, you should be thinking, I could have made the bond between the carbon-carbon bond between the alpha and the beta carbons through the aldol reaction, through attack of an enolate on a carbonyl. Okay, other questions so far? Yeah.
Why do we call it alpha and beta relative to the enolate?
Why are we putting alpha and beta relative to the enolate? No reason other than I think way back when you learned about nomenclature, ketones have a little bit higher priority than alcohols, and so I think that's where we start counting for that reason. There's no reason why you couldn't count the other way. Okay, others? All right. Often the reaction doesn't stop here, but continues on to an alternative product, and you need to be able to recognize both as products of the aldol reaction. And what can happen at this stage is, if you notice, the aldol product still has alpha protons, and they're still in that last step. We just regenerated base. In fact, the aldol reaction is base catalyzed. So the base can remove the alpha proton again, or remove the alpha proton from the aldol product. That will generate this enolate. Now, your initial worry could be, how do I know, is that enolate going to go react with some additional carbonyl starting material to get an even more complicated product? At least it seems like a reasonable possibility, but your text doesn't have us worry about that, so we're not going to. What actually happens once you form this sort of what I guess we could call second enolate is an elimination reaction where electrons on the alpha carbon kick down and kick off the hydroxy group on the beta carbon. And that generates what's called a dehydrated product, where relative to the beta hydroxy carbonyl compound, we've lost water. Again, I'm going to label stuff according to what we've done before. Here is the portion of the molecule that used to be the enolate. Here is the portion of the molecule that used to be the carbonyl carbon. Here's in pink what used to be the carbonyl oxygen, and that gets kicked off here as OH minus. And this is also an aldol product. It's the dehydrated version of the beta hydroxy carbonyl compound. It's also, you will recognize, an example of an alpha beta unsaturated carbonyl compound. Yeah.
In other reactions, we've had to convert that alcohol into a good leaving group by making it water, essentially.
Right.
Why don't we have to do that here?
Why is it possible for this to leave as OH minus? And the answer is, whenever we've considered can a leaving group leave, we've compared the sort of strength of the kicker offer to the reactivity of the group that leaves, okay? So in this case, the leaving group was OH minus. The kicker offer was an enolate. So we can compare the ability of a kicker offer to kick off a leaving group by comparing the acidity of the corresponding conjugate acids. Okay? The leaving group is OH minus. Its conjugate acid is water, pKa around 16. What we want to know is OH minus more or less reactive than the enolate that does the kicking off? Okay, so the enolate has a conjugate acid whose pKa is 20. So that means it is a strong enough kicker offer to kick off the OH minus. Yeah?
So will it always go on to the dehydration product?
Will it always go on to the dehydration product? The answer is, I think your text hedges on this point because reality is it depends. And I understand that's uncomfortable because you want to know what the right answer is. And the right answer is these are both correct aldol products, and whether you go to one versus the other is going to be context dependent. Things that can favor the the ratio of one product to the other, the beta hydroxycarbonyl to the alpha beta unsaturated, is going to be determined by their relative stability because they are in equilibrium. So you could maybe imagine some things that might favor one versus the other. One thing that can favor the alpha beta unsaturated carbonyl compound is if there are other groups attached to the beta carbon that might be conjugated to the double bond here and ultimately to the carbonyl if we did the dehydration. So that's one of the factors. So naturally, you're not going to be put in a situation where you're supposed to predict the product and this or this will be the wrong, one of them will be the right answer and the other will be the wrong answer, okay? It'll be either of them are okay. Naturally, you're going to want to know, well, do I select both? And I promise not to put both of them as options on a predict the products question, just one, okay? But you need to be recognized either because you don't know whether I'm going to do the one or the other. In a mechanism, of course, you'll know where you need to end up because in mechanism questions, the starting material is shown and the product is shown, so you'll know what you need to do. In a synthesis question, you are free to use either of these as viable products and intermediates to use in subsequent steps. For example, we learned in Chapter 13 a couple of things you can do with alpha beta unsaturated carbonyl compounds. We learned about conjugate addition of cuprates to the beta carbon, and that's something you can do with these. Okay, good. Other questions? In a retrosynthesis sense, if you're looking at the beta hydroxycarbonyl compound, you should be able to look at this and think backwards to what the starting material was. In a retrosynthesis sense from the alpha beta unsaturated carbonyl compound, you should recognize that both the sigma bond between alpha and beta carbons and the pi bond between alpha and beta carbons are the ones that were made during this process. And the purple portion was the nucleophile, the enolate, and then the blue carbon was the electrophile, the carbonyl carbon. You can tell whether it was an aldehyde or a ketone by looking at the two other things that are attached to the beta carbon. All right, so let's actually try that in a retrosynthesis sense. I'm going to show you a product, and we'll make this bad even from the beginning because it's going to involve a six-membered ring. But hey, at least we like six-membered rings because they're easy to draw hexagons. All right. So here is a product, and I'm telling you, you could have made this via the aldol reaction. And so you need now to fill in the starting material. So the way to do this is to focus in on the structural pattern that we talked about. What do you notice about that product? Which of the two aldol product structural patterns does that one meet? The alpha beta one, the alpha beta unsaturated carbonyl compound. Here is the carbonyl, here's the alpha carbon, here's the beta carbon. Okay, that tells you which two bonds did you make in this reaction, in this aldol reaction. You had to make the sigma bond and the pi bond, right? So then which carbon was the carbonyl carbon in the starting material, the electrophile? Beta, right? And that means which carbons were involved in the nucleophile? Where was the enolate? It's on the other side, on the alpha carbon, right? Okay, good. So at this stage, thinking backwards, I'll use a squiggly line to indicate where the disconnection is. I'll just redraw this molecule, and I'll just go backwards to the enolate. We'll go backwards just one step to the enolate. The negative charge is going to be on the alpha carbon. Then I'll draw everything else exactly the same way. This is the thing that becomes the beta carbon, and I've already said that it's going to be my carbonyl carbon. What does that beta carbon need to have on it now? It's going to be the electrophile, so it needs to have that. All right, and I've jumped several steps actually. I've jumped to what the starting material is. If you want to think backwards just one step, the intermediate that's previous to the alpha beta unsaturated carbonyl compound is this one, where you have an OH on the beta carbon. Because remember, that's the one that gets, the OH is the one that gets kicked off in that final step. And if you want to think back a step further from that one, that would get you to the beta hydroxycarbonyl compound. And then if you want to think a step backwards from the beta hydroxycarbonyl compound, what you would have based on what was above was the negatively charged oxygen. And then that's what you get from when this enolate attacks the carbonyl carbon like this. Does that make sense? So the starting material would just be the conjugate acid of this enolate, which we could draw here. Just look like that. Or alternatively, if you wanted to draw it in a sort of zigzaggy sense that doesn't make it sort of obvious where the six-membered ring is going to form, you need a 7-carbon chain, 1, 2, 3, 4, 5, 6, 7, with ketones on either end. All right, so that's the correct starting material for this aldol product. Yeah?
In this case, how would you like selectively deprotonate that alpha carbon? Because if you were to use like LDA, wouldn't it take both protons on both sides?
Okay, yeah, so I think your question is related to if this is my starting material, what if I deprotonate 7 instead of 1?
Like, how do we selectively choose just to deprotonate 1? Like, I know you can do 1 equivalent, but that's very...
Right, and the answer is it's even more trickier than that. I mean, I think your question is, first, let me answer the question of what if I deprotonate 7 rather than 1? So just to get us all on the same page, I'm going to number the atoms like this over here. And the quick answer there is that this proton here on gray carbon 1 is actually identical by symmetry, to this proton here on gray carbon 7. So it actually doesn't matter which one I deprotonate first. I deprotonate one of them, I make the enolate, and then the subsequent reaction where the enolate attacks the carbonyl compound is intramolecular, and because of that it is fast, and so I don't have to worry about if I deprotonate a second. The other thing is, once the molecule itself already has a negative charge, the pKa of the other proton goes up, because then if you deprotonate it again, you'd have one molecule with two negative charges and there'd be charge repulsion. Okay, so that's the first issue. Go ahead.
If it was asymmetrical, would you get two products?
If it was not symmetrical, could you anticipate two products? Yes, and the relative ratio of those two, because this is an equilibrium process, should be dependent on which one was more stable. And we're actually going there because one thing you haven't mentioned, but that may be on your mind, is there is another alpha proton. And of course, I'm not going to point out that the carbon 5 has an equivalent alpha proton, all right? So I want you to think through, and I'm going to copy this down because we're going to consider this possibility and we need a little bit more space. You've seen the product that comes from removing the orange alpha proton. Oops. I'll just draw that enolate one more time. And you can see that if this orange alpha proton attacks our carbonyl carbon on carbon 6, that's what gives us the 6-membered ring product that I showed you before. And we're not going to redraw the whole reaction or the whole mechanism because you've seen that. But that's what is going to give us this product, where this is 1, 2, 3, 4, 5, 6, and 7. Okay? But now I want you to consider what happens if I remove the purple alpha proton. And then we're going to count and see how many atoms away that carbonyl carbon is. This is carbon 3, 4, 5, and 6. That's 4 atoms away, right? So if the purple alpha carbon attacked the carbonyl carbon, what kind of a ring did I just make? 4-membered ring, right? So to draw that, and we'll just skip ahead a few steps. To draw that, I'm just going to draw a square. I'm going to pick an atom to be atom 6, the carbonyl carbon. Let's just have that be this one. That means this one is 5, this one is 4, and this one is 3. Carbon 6 used to be the carbonyl carbon. That means in our aldol product, that's going to have an OH group on it and carbon 7. Carbon 3 should also be attached to carbon 2 there. Okay, and then if we went on to the alpha beta unsaturated carbonyl compound, this would be our product. Okay. Do you see those two options? Go ahead.
For that last dehydrated product to form, wouldn't the base have to deprotonate a tertiary carbon? Isn't that like very unlikely, unstable?
You're pointing out that in order for the dehydration reaction to happen, the base would have to remove this proton. Protons are relatively accessible. OH minus, even on tertiary carbons. In 351, you did eliminations all the time from tertiary carbons, and in some cases it was great because it leads to a more substituted double bond. So sterics aren't a major issue here. The major issue, though, is the relative stability of the products. So there's a point that we want to make here. In Chapter 17, we made a big deal out of which enolate you form a greater amount of based on the conditions. And we said that under equilibrating enolate conditions, enolate formation, you get the more substituted enolate as the major enolate. So, which of these is our major enolate, orange or purple? Orange. Nevertheless, which is the major product, purple or orange? You're not sure what to say, are you? Because you're like, the major enolate is the more substituted one, but what problems do you see for the purple product relative to the orange product? Steric hindrance, right? Steric hindrance is maybe not the right word that I wanted to say. I wanted to say angle strain or ring strain. You've got a double bond in a 4-member ring. Those bond angles want to be 120 degrees, but they can't be. They're forced to be 90 degrees. That's quite a bit of ring strain. So even though product that's purple is the more stable enolate, the product it leads to happens to be the less stable product. And even though the orange enolate is the less stable enolate, it leads to the more stable product. And this highlights an important point, which is that when products are in equilibrium with starting materials, the only thing that matters is the relative stability of the products. The enolate stability doesn't actually matter here. The reason the enolate stability mattered in chapter 17 is because after we formed the enolate and did the alkylation reaction, that alkylation reaction was irreversible. So the amount of each enolate present determined how much alkylation should occur. In this case, even if we formed, even though we have more of this enolate present, more of the material is going to be drawn to this lower energy point. And I'll make that point with an energy diagram that we can draw. Here is, let's see. We'll put the aldol starting material here. And we'll put the purple enolate, which is more stable, here, lower in energy, than the orange enolate, which we'll put higher up. But then we'll show the product from the purple enolate as being higher in energy than the product from the orange enolate. Such that this is kind of our, and this is probably exaggerated, but this is sort of our energy diagram. We can go up a hill to the more substituted, more stable enolate on this side, or up a hill to the less substituted enolate on this side, but the less substituted enolate leads to the more favorable product. And because products are in equilibrium with starting materials, even though it is true at any given point there's more of the purple enolate than the orange enolate, over time we tend to form more of this more stable product. Yeah.
If carbons 1 and 7 didn't have hydrogen, then would you expect the purple?
Sure, if you didn't have any hydrogens on 1 and 7 and there was no other alpha protons, then yeah, we wouldn't be surprised to see the purple product. All right, and I'm just going to put this one as the major product to make that point. Okay, others? So what we've just done is called an intramolecular aldol reaction. That requires a little bit of practice, and you should do some problems in the study guide and in the book problems to help you with that. But in general, you're going to predict products based on what gives you the more stable ring size, where 5 and 6 membered rings are more stable than 4 or 3 membered rings. Okay, other questions, thoughts on that? Yeah.
Do you ever see the electrons in the layers resonate up into the oxygen, so the oxygen doesn't?
Yeah, do you ever see the oxygen of the enolate do the nucleophilic attack like this? The answer is, for the most part, we see enolates react on the alpha carbon because that's where more of the HOMO is. You can do the MO theory calculations, and they say that even though this looks like a better resonance structure, more of the high energy electrons are actually on the alpha carbon than on the oxygen. That being said, sometimes you can see, not in the aldol reaction, but sometimes you can see in enolate alkylation where you're showing an alkyl halide be attacked by the enolate, you sometimes see the product of alkylation where the oxygen does the attacking. Not always, and if you see it, don't be concerned or worried by it. For the most part, if you're predicting it, the enolate will react on the alpha carbon. Okay, others? Yeah.
So is the base that's removing the alpha proton that LDA in this situation?
No, the base that's removing the alpha proton is just OH minus. You could use LDA, and you'd be more comfortable using LDA to selectively remove the less substituted proton. It turns out, though, you don't need to, because the product that you get from removing the less substituted proton is the more stable one. Yeah, good. What else? All right, so now we're going to do, we've done an aldol reaction of a ketone with itself. We will call that a self-aldol reaction. We've done an intramolecular aldol reaction. And I want you to remember the intramolecular aldol reaction because we're going to come back to it in this chapter to make a ring that's very much like the one we just made. And I want you to just see that at that point as, oh, that's just an intramolecular aldol reaction. What we're going to do now is ask the question, what if you wanted to bring two carbonyl compounds together, but they were not identical? So we're going to call this the cross-aldol reaction. And the question we're going to ask is, can we control who is the nucleophile versus who is the electrophile? So let me give you an example of this. Let's imagine taking this ketone and then this aldehyde. We're just going to keep it pretty simple. And we're going to say that, we're going to imagine all the things that could happen if we put these together with a small amount of base. Why are we using OH minus, by the way? The answer is it's cheap and the reaction works. This reaction, if you've followed along, is actually catalytic in base. We use OH to make the enolate at the very beginning, like I showed you here, and at the very end we generate OH. So it turns out you don't need to waste your time spending a lot of money on LDA when a catalytic amount of a very cheap base will work. But let's just predict what would happen if we brought these two things together. We've got a ketone and we've got an aldehyde. Let's draw the enolate that could come from the ketone. That's this one. Now let's draw the enolate that could come from the aldehyde. That's this one. So I'm going to label the ketone in purple, not because that's our color for nucleophiles, just because I need a color to keep track of the carbons that came from the ketone. And we're going to label in orange the carbons and stuff that came from the aldehyde. So now you can see our problem, that because at any given time I have the purple ketone and the purple aldehyde, the orange aldehyde is electrophiles. And then I have the purple enolate and the orange enolate as electrophiles. So I'm concerned about multiple possible reactions. I can think about the purple enolate attacking the purple ketone, or the purple enolate attacking the orange aldehyde. Then I have to worry about the orange aldehyde attacking the purple ketone and the orange enolate attacking the purple, sorry, I'm getting so confused. The orange enolate, are you with me? Should we try that again? I'm worried about self and cross reactivity. Ketone enolate reacting with ketone electrophile, ketone enolate reacting with aldehyde electrophile. Aldehyde enolate reacting with ketone electrophile, aldehyde enolate reacting with aldehyde electrophile. In other words, when I try to do this cross-aldol reaction, I kind of get a mess of both self and cross-aldol products in all combinations. So, for example, this would be the aldol product, and I'm just going to do, for this example, I'm just going to draw, to keep it simple, I'm just going to draw the beta hydroxycarbonyl compound. I'll try to highlight the new bond we made in red. Here is the self-aldol product from the ketone. You can see the two ketone portions that are together. Here is the cross-aldol product using the ketone enolate to attack the aldehyde electrophile. In red is the bond that we made, and then in orange is, the aldehyde portion. And then we'll just do the same below. Here is the product of the aldehyde reacting with itself. This is the self-aldehyde product. Here in red is the new bond that we made. In orange is the aldehyde enolate, and then the aldehyde electrophile portion. And then here, lastly, will be what we get from having the aldehyde enolate attack the ketone as an electrophile. Here's the portion that came from the ketone. Here's the portion that came from the aldehyde. So you can see the problem, all the combinations. And that's not to even also say plus the dehydration products, and there would be 4 more of those. Okay, so the crossed aldol is kind of a mess unless you try to take control over who the nucleophile is and who the electrophile is. So I'm now going to give you just a few ways that you can take control of who the electrophile is versus who the nucleophile is. Controlling the crossed aldol. So one possibility is choose an electrophile that lacks alpha protons, because then you can't make the enolate from that one. So here's an example of that. Imagine we still use our standard acetone as our, with an alpha proton to make our enolate. But imagine that the other partner is an aldehyde that lacks alpha protons. So this is a molecule called benzaldehyde. No alpha protons, so you can't make an enolate. So this one can't be the nucleophile, it has to be the electrophile. So you could hope to get mostly the desired, and I'm going to use pH to abbreviate the benzene ring. Here is the bond that we just made. In orange is the portion that was the aldehyde electrophile. In purple is the portion of the molecule that came from the nucleophile. You can hope to get this cross-aldol product and none of the potential cross-aldol products where the aldehyde becomes the enolate, because there's no way to make the enolate there. Of course, you would also get the dehydration product, which I'm not drawing, but which you could draw. It would just be the alpha-beta unsaturated carbonyl compound. Now, there's still a problem with this. What is it? Can the purple one still react with itself? Yeah. And so you would still expect to see the purple self-aldol product. And so, if you were to try this in the lab, you would not be surprised if you got a mixture of both of those things. Okay? So the second workaround for the crossed aldol reaction is to choose to make your enolate from a carbonyl compound with crazy acidic alpha protons, such that you can't even imagine making the other enolate. An example of this would be to start with one of these beta dicarbonyl compounds where the pKa of the proton that's alpha to 2 carbonyls is around 9, and then to have your other partner, let's have it just be this aldehyde. The aldehyde still has alpha protons, but the aldehyde alpha proton has a pKa of 17, whereas the beta dicarbonyl compound has a pKa of 9. So in the presence of base, it's actually no contest. You form 100% of the desired enolate. And that's great because at that point, none of the purple carbonyl compound remains to react with itself. So the only thing that can happen then is for the purple carbonyl compound to react with the orange aldehyde. And that crossed aldol reaction works pretty well. So again, just to save time, I'm going to draw for you the aldol. We'll skip ahead a few steps. I'm going to draw for you the new bond that we formed. I'll label the portions of the molecule that came from the aldehyde electrophile versus the beta diketone nucleophile. And instead of drawing the dehydrated product, I'm just going to make a note that you would also expect the dehydrated product to form. Okay, questions there? The last workaround that you can do, and this is going to be the one that I think you will like the most, your text calls the directed aldol. And the strategy here is make one enolate quantitatively, that means with 100% yield, using LDA, and you do that first. And then, and only then, in a second step, then you introduce the carbonyl electrophile. And you keep the reaction cold to prevent the one enolate you just made from deprotonating the other carbonyl compound. And if you're careful, it'll work well. I will illustrate that strategy for you next time. At this point, I am sick of drawing, and I think you are too, so we're going to call it good. All right? See you on Wednesday.